We're going to continue building on our work in section 10.1. We're going to try and find what's called a regression equation, and that is basically fitting a line to our data. So we saw some data of various things in the last section. Here's one that's kind of interesting related to stuff we were just talking about. That is, there's an app called Flixter. And what Flixter does is it shows you previews of movies. It gives you dates and times and show places. But also shows you ratings of critics and ratings of users. And it's kind of interesting to compare the two. So the ratings of the critics is along the x-axis. The ratings of the users is along the y-axis. So in general, it seems like there's a loose correlation between the two. You know, they're not always spot on. They tend to be a little bit better in the higher regions. That is, if a movie is really good, both groups tend to like it. But the critics can be really harsh, while the audiences can be pretty generous. Like, yeah, no, we like that. I don't care what you say. So what we're going to move on to is trying to find a line that represents this data. So this line, that's a summary line, it's called the least squares regression line. So let's talk about that over here. Now your sample statistic for this is y hat equals b1x plus b sub 0. So you're going to learn your regressions. You're going to learn about linear equations. We'll go through that in a minute. But you're also going to relearn or learn some of your Greek letters. So the population parameter, remember this is your statistic estimate, this is your population parameter, is y equals beta 1x plus beta 0. So as a reminder, this line is in slope-intercept form. So let's take a look at what that means. Let's go back to here. Let me just add in a couple things. So I'll add in a quick expression. Let's do y equals mx plus b. Because that's essentially what we have here. And now, what do these things mean? Well, what's m mean in these types of equations? Do you remember? Yeah, the slope, the rise over the run. And the slope, let me change the slope here of this line. Here's the slope. That changes how steep the line is. And the y-intercept here, that changes how, where the graph crosses the y-axis. Let me just change this just a little bit. Let's go up to, say, 80. So let's raise this up here. Now what can happen is that depending on your data set, once you fit your curve, sometimes it might be that you have a slope of 0. Now a slope of 0, let's make that a definite 0, essentially means you've got a straight line, a horizontal line, and that your line that best predicts your data is really nothing more than the average of the data. So that's as good as you can do. So that's why in section 10.1 we were testing whether or not rho is equal to 0. Rho equals 0 is equivalent to the slope of this line is 0. All right, so our new hypothesis test is going to be whether or not the slope is significantly different than 0. So let's go back to that. So this is our hypothesis test in this section. That is h sub 0 is that b1 or beta 1 equals 0 versus the alternative hypothesis that is different than 0. If you have a slope that's significantly different than 0, then knowing the value of x helps you predict the value of y. Yes, sir. Yes, beta 1 is your slope. Thank you. So let's go back to problem number 22. Hopefully you saved your data in StatDisk. Problem 22 was is trying to find a relationship between the number of times a cricket chirps in 1 minute and the temperature. So a quick look at that again, and then we'll work on the data. Oops. So here's your data. We're going to enter this data. Hopefully we already have it. And then try and make a prediction as to, what the temperature would be if you have 3,000 chirps in 1 minute. What would the temperature end up being? Okay, so this data is already in StatDisk for us here. So I'll get rid of that. It's in columns 4 and 5. So let me go to analysis, correlation and regression. Significance level, we'll leave it at 0.05. Again, I want columns 4 and 5. It might be different for you. Once you get this set up, let's click Evaluate. So there's a couple things we can do in terms of our test. We'll test this a couple ways. One of them was with setting up things and using the table for R, which I still owe you from the last video. One of these days we'll remember it. But more directly, what are most of you going to do to decide whether or not to reject HO or HA? P-value. So the p-value in this case is what? 0.00462. 0.00462. So what does that lead us to in terms of a decision on HO or HA? I should say HO. Yeah, thank you. Yeah, we're going to reject. Reject H naught. Now, if we're testing for whether or not we have a significant relationship, this would be our original claim. But I want to focus on something other than stating the conclusion in words. Let's look at the model that we get out of all this. So the model is going to be denoted by y hat. And let's look at what y hat is. Y hat, that's your predicted value. It's going to equal sum mx plus b. So like I said, y hat is your predicted value. Let's pick up these numbers from the output in StatDisk. Can anyone find what the slope would be? Good. 0.0524 times x plus 27.50 for y. Yay! So that's our regression equation. And this is what you can use to make predictions. Now, accordingly, we've got a significant regression here. Let's just take a quick look at the scatter plot and see what that looks like. Yeah, it looks pretty good. I mean, I think knowing the value of x does help us with knowing about what the value of y is. Some are better than others, but overall it does give us a good estimate. There's one last thing that we're asked to do here, and that is make a prediction. Is what if you had a cricket chirping 3,000 times per minute? What would the temperature be? Well, probably one hot, tired, overworked cricket, but let's figure it out. 0.0524 times 3,000 plus 27.50. Let's give that a shot. $184.7. Does anyone see a problem with that? Yeah, the cricket would be dead. I would be dead if I had to sit there and watch it. Yeah, that's really, really hot. Okay, and the other problem is that this value is really well outside our data. And so you have to be careful. It goes beyond this course to investigate it, but there's ways you can investigate, well, how, what kind of a confidence interval can we surround this prediction with for something like that. And once you're getting that far past your data, I mean, look, the highest value we've got is 1200. You're doing something, making a prediction for something that's double that. Yeah. You can make predictions for the near future, 1300, maybe 14 or 1500, etc. But once you're getting out much beyond that, then it's a little bit risky. You don't know if this relationship holds beyond what you've got in your data. So you can make predictions, but they may or may not hold up. Okay, how are we looking with problem number 22 there? Good? Let's go back to the output here. There's a little bit of something here that was written, but not really said. We didn't talk about that. It's called the coefficient of determination, r squared. It's down here. So let's talk about what that is. Coefficient of determination, and that's your r squared. Coefficient of determination equals r squared. And the choice of notation here is not an accident. The choice of notation here is intentional because there's definitely a relationship between r and r squared. But let's first understand what r squared tells us. So r squared tells us the ability to explain y by knowing x. That's a very informal definition. The ability to explain y by knowing x. And one of my students in my morning class actually happened to use that one, and I liked it. So that's a nice informal definition. Let's give you something a little bit more formal and to the point. So that's informal. A little bit more formal would be the percentage of variability in y that is explained by knowing the value of x. Percentage of variability in y that is explained by knowing x. Okay. Now, the one thing that goes along with this is something you could probably figure out if you spend a little time thinking about it. And that is, r squared has to be between 0 and 100%, or in decimal forms between 0 and 1. So those are the limits on r squared. You can't do better than explaining 100% of the variability. You can't do worse than explaining 0% of it. So it's between those two values. Let's go check this out. We've got some output here. So we've got our value of r squared. If I know what r squared is, how do you think I could get r? Yeah, take the square root. So let's take a look at that and see if that works. So we'll take the square root of 0.76249. See what we get. So clear that up. Square root of 0.76429. 0.874. Let's compare that to r, which was the linear correlation coefficient. And it matches pretty good. Did I type in something wrong here? 0.7624. Yeah, yeah, I did round a little bit. Makes a bigger difference on this. Well, I guess that makes about sense. I did round a little bit. Yeah. Or you can do things the other way. If you know what r is, you can take this and square it and get the value of r squared. Let me do one other thing with the output here. You've got this measure of total variation. So that's the total variability, and that really kind of reflects this kind of a total. Let me put that up here. So your total variability would be the sum of your y, your observed values, minus the mean y bar. That's your total variability. So that total is 462. The part that it's explained by the regression is how close your predicted values are to the mean, or how far away they are from the mean. And then there's the unexplained, the difference between your observed value and your predicted value. So if you wanted to get the whole picture on this, it'd look like this. Sum of y minus y hat. This is your unexplained variability. And then the last part is your explained variability. So it is y hat minus y bar. Explained. And these should all be squared. If I take this total and divide it by this total, I'm going to get my r squared. That's just the mean, y bar. That's just the mean of the y values. Yeah, thank you. So looking back at this, if I take the 352.89 and divide it by 464.82, this should give me my approximate value of r squared. So let's check that out. 352.894 divided by 462.8187. That should give me my r squared. Yeah, pretty good. So 0.62. And that's where it comes from. Now, if you ignore the squares and all this stuff, you can kind of understand this relationship a little bit better, and you'll see some of the cancellation. If you got a minus y hat here and a plus y hat here, these kind of cancel each other out. And we give you y minus y bar. All right, so anyways, there's some nice mathematical trickery that can show this more accurately. But this is what you should know. You should know that r squared measures how well your variables are doing in predicting the y value. Yeah. It's no longer just limited to a linear relationship. R squared can evaluate all kinds of models. Let's do another one with some data. Let's take a look at Old Faithful. Where are you going to find Old Faithful? Yellowstone, yay. It's a geyser. Yellowstone has more active geysers than the rest of the world combined. So, kind of a neat little hot spot there underneath the Earth's crust. And based on the time between intervals, duration of eruption, maybe we can make a prediction for how long it'll be before the next eruption. So we'll see. Let's see how good we can do. Let's start by entering the data. So we'll go to stat disk. I think I can get rid of these. Yeah, I'm just going to type over these. So our interval times would be 242, 255, 227, 251, 262, 207, and then 140. Actually, that's the duration. That's how long in seconds that these last. And then over here, 91, then 81, then 91 again, 92, 102, 94, and 91. Let's take a quick look at our data, see if we think that there is actually a linear relationship between these two. So I'll just do a scatter plot. You can also do that from the regression menu. That's not a big deal. What do you think? Does it look like there's a meaningful relationship here between the length of the eruption and how long you have to wait for the next eruption? No. The slope here is pretty close to zero. I mean, they fit a line for us even though we didn't ask them to. That's all right. Let's actually do the calculation. So we're going to do a hypothesis test as to whether or not there's a significant regression. That is, the slope of the line here is significantly different than zero. So we're going to test H naught such that beta 1 equals 0 versus the alternative that it's different than 0. We can test this at the 5% level because they haven't given us anything. Alpha is 0.05. Let's go with the original claim here. All right, so let's jump up to step 4. Get a p-value. Analysis. Correlation and regression. Evaluate. So we get a p-value of 0.9213. Abby, we're going to reject H naught or fail to reject H naught? Yeah, fail to reject. This one fails in a pretty big way, so it's another epic failure, but definitely fail to reject H naught. So realistically, if you're rejecting H naught, then what it's saying is that if you're going to make a prediction about this data, that is, if you have an X value and you want to make a prediction about the Y value, then really you should just use the mean or the average of the Y values. That's what it's saying. It's like, you know what? Your best guess is just the mean. That's kind of summarized here for you in your book, page 492. So making predictions at the bottom. It's essentially saying this: if you've got a significant relationship, use a relationship. If you don't, then essentially you just use the sample mean. And that's the mean of the Y variables. So for a good model, then you can use the regression equation. Now, your computer is going to always calculate a regression. It's going to give you, a B1 and a B sub 0. It doesn't mean you should use them. And in this case, if you're rejecting H naught, or if you fail to reject H naught, You should just be using the mean. Yeah, and you can see from the slope of that line, it looks like there's not a whole lot going on there. Now, I promised several times today, and before I forget it again, let's actually do it. There's another way you can do these hypothesis tests, and it's the step 3 that I always skip. So let's take care of that right now. Step 3 is to set up a critical region. That is an area where your test statistic says reject, and another area where it says fail to reject. So reject H0 and fail to reject H0. Now the nice thing about StatDisk is that it actually gives you all that you need to set up this region. Let's take a look back at the output. So that's over here. I don't need this anymore. Okay. Our test statistic is going to be right here. Is the value of the correlation coefficient itself, 0.0463. So that's your test statistic. So let's write that down. 0.0463. Now it sets up a rejection region for you. It tells you the critical value, and this is going to separate the rejection region from the fail to reject region. So let's write down this next value as well, 0.7544. Now they give you a plus or minus 0.7544. I'll tell you why when we get to the tables. But this is going to be the dividing line between reject and fail to reject. So over here is 0, over here is 1. So the closer you are to 1, the more significant of a linear relationship you have. Our test statistic was 0.0463. So it's pretty far away from the rejection region. So we didn't come close to rejecting this. And we saw that in the p-value. Now, if you didn't have StatDisk, you could get that number from the back of your book. It's table A6. So I'm trying to remember, is it page 690 something? So I think where that's at. Yeah, 692. It tells you exactly how to do this test. Down at the bottom of your table, it says we're testing no correlation against a correlation. So essentially a flat line versus a line that has a slope. And you're going to reject if the absolute value of R is greater than or equal to the critical value. That's why, and I'm not going to show you all the math, but that's why there was the plus or minus. You're going to take the absolute value of R and compare it to the value that you get from this table. Now, how many observations do we have for our current data set? Let me look back here. So, how many pairs? 1, 2, 3, 4, 5, 6, 7. So, 7 pairs at the 0.05 level gives you a critical value of 0.754. So anything above this, you reject H0. Below this, you fail to reject H0. And that value for the 0.01 level is 0.875. All right, a little bit more than what we typically need. There's nothing wrong with basing your conclusion based on the p-value. In this case, there's not a significant regression. The last thing I'd ask you is, how does says find the best predicted time for an eruption with 253 seconds. So even though we didn't really find a significant regression, we did get output from a regression. Our model is y hat equals 0.00673 x plus 90.1 0.19. So just using these two values here for your slope and your intercept. Or right here. So if I wanted to make a prediction then for, where is it, 253 seconds, that would mean plugging in a 253 here. 0.00673 times 253. And let's see how that does. Now notice what multiplying 0.00673 times 253, this part gave me 1.70. It's not really affecting the overall prediction all that much. So if I add 90.19 to that, I get a predicted time of 91.89 minutes. The book says that the actual interval in this case was 83 minutes. So about a 9-minute difference. Fairly substantial. I'm not sure how annoyed I'd get waiting there, but it's a fairly substantial difference. It's not a great prediction. Okay, we're going to do some more of this on Monday. Let's see. Is there any comments or questions on this stuff here? Charbel, usually you got something to say. Go ahead. Don't disappoint me. What's the homework? All right. Homework. Let's try 1 through 17. We're going to spend some more time on this on Monday, including some work, some hands-on work with some data regarding temperatures in Michigan. Austin?
2 questions. Is that for the competition too?
Yes.
We don't have quizzes or whatever today, or
There is an extra credit assignment that I'll talk about in a minute. But is there anything else? Anything else regarding regressions? Okay.